Hello and welcome to another video. In this problem, we're going to be doing the second problem of yesterday's LeetCode contest, and it's going to be separate black and white balls. So there are n balls on a table. Each ball has a color, black or white. You're given a zero-index binary string S of length n, where 1 and 0 represent black and white balls. In each step, you can choose two adjacent balls and swap them, return the minimum number of swaps to group all the black balls to the right and the white balls to the left. So we have this example here. So we are trying to get all the ones basically to the right and all the zeros to the left. So we need to do one swap here, swap the 0 and the 1. In the second example, we need to get the 1 all the way to the right. So we would do a swap once to get in the middle and one more swap to get it to the right. And in the last example, they are all already perfectly grouped. So the key to this problem is realizing what is the actual optimal way to do the swaps, and then is there a way to do it quickly? Because once again, if we look at the constraints and try to figure out what algorithm to use, this is a 10 to the 5th length. So we have to use something that's n log n or better, or the other dimension, if we do something like dp, has to be small. We can't have like an n squared algorithm. So once again, for n log n, the main things you're going to want to look for is something like a 2-pointer or sliding window, very common, or like maybe a binary search. So let's actually build some intuition for this. And let's try to actually have some examples and then figure out exactly how it works. And actually what we're going to start with is we're going to start with just one ball. Okay. So let's say we have one ball, well, one black ball and the rest are white. So let's say we just have something like this. One. And so the idea is we want our final thing to look like the one is over here, right? So we know exactly where the right ball needs to be. We know the exact location. It needs to be here. And can we figure it out quickly? Can we figure it out without doing the swaps manually? Well, we can, right? Because we know, if this has indices, we know that we are trying to get to here and we are here. So we need to do 3 swaps, right? Each swap will move it to the right one time. And notice the swaps aren't really affecting, we don't really care about the other numbers because we're just moving zeros around, right? Assuming all the rest are zeros, it would be problematic if there was a 1 here. Let's say there's a 1 here, and now you do these swaps. You can't just say okay, well, let me figure out how to get this 1 over here. Because the problem is, if you actually do, let's do these swaps actually. So if we swap, right, this will become a 0, this will become a 1. And now we have a 1 and a 1, and we're trying to get this one over here. So then if we swap again, we get 1, 1. And then if we swap again, we will get, so if we swap these two, it's the same, right? But then we have a 0 here. If we do a swap here, we actually get this. And so the problem here is that even though we got this one to the end, we moved this one, right? Because every time you do these swaps, all these other things move to the left one, essentially. And so that's problematic. So we need to ensure, essentially going back to this problem, that whenever we do these swaps, if we swap one with only zeros, it's totally fine, because then we'll just have a bunch of zeros and then the one will be in the end. So for this one, for example, if we only have zeros and we say, okay, well, we need to get here. So it's going to be 3 swaps. So essentially what it's going to end up looking like is it'll look like this, right? But like I said, we notice the problem that if we have some 1s and then we try to get one of our 1s to go past another one, that's a problem. But luckily for us, in the optimal solution, you're never going to need to have a 1 go past the 1s. You're only going to be swapping 1s with zeros. And let me show you how that's going to be. So let's say we have 2 1s now. Instead of this one, we have 2 1s. So let's say we have this one and this one. So there's a few ways to handle this problem, right? We know our 1s need to be here, and basically what's the best way to do this? What's going to have the least amount of operations? Well, one of the ways is to just get this one over here and then this one over here, right? That's one way. And it's also going to be the easiest, luckily for us, that is the optimal solution. And it's also going to be easy with swaps because essentially what's going to happen is all of these zeros will move left, right? And the 1 will just be in the 0 spot. But luckily, if all the zeros move left, we don't have to represent that in any way. It'll look the same as just putting the 1 over here. So once we get this one over here, then we know this one needs to go over here, and it's the same thing. All these zeros do move left, but luckily for us, that looks the same as just swapping these two things here, and we can do it in O of 1 time. Now, the other way would have been to maybe like have this one go in here, and that would actually be worse because what's going to happen, like let's actually count out how long both these ways take. So the first way that I originally said, this is going to take 3 swaps, right, to get from 3 to 6. And then once our 1 is over here and our 0 is over here, then we need to get this one over here, and that's going to take 4 swaps, right? And like I said, if you're only swapping 1, 1 and your entire path, you want your entire path from your 1 to get to the end to be all zeros, because then you're not moving any of your 1s backward, right? Essentially, you're only moving zeros backward. So this takes, this one was over here, so we move 1, 2, 3, 4, so this is 7. But if we go the other way, where we have our first number, like if we have the 1 over here, and we try to move this one over here, because you might think like maybe it's equivalent. So this right here will take 1, 2, 3, 4, 5. Right? But the problem is that you would have moved this one back 1, because anytime you do a swap, like I said, anything you swap with moves back 1 essentially. So what it's going to end up looking like is like this now, and then this would take 1, 2, 3. So it would actually be 8. So the optimal procedure is, going back, we can write it down, is take the rightmost one and put it in the rightmost available spot, or a rightmost spot, and then keep going, right? So essentially, we take this one, we put it over here, we take this one, we put it over here, and we keep doing this. So let's actually walk through this problem with like a bigger array with more 1s essentially. But the nice thing about this is we don't actually have to like do swap by swap, because we know everything that we swapped with is going to move left 1. But if it's only zeros that we're swapping with, then it's basically going to say all our zeros move left 1, and then our 1 just takes the rightmost 0. So we can just do that in O of 1 time. We can just say like, okay, this is 0 now, and this is 1, right? And we don't even need to actually, we don't even need to change it to a 0. We'll just simply say it's the available spot. So now I'll kind of show you how this works with a bunch of 1s. So let's do a dry run with a bunch more numbers. So let's say we have like 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, let's say. Okay, so now let's index these and let's walk through how this will work. And yeah, like I said, I think it's just good to draw out a couple of examples, and then you can really get the intuition of like the optimal way to do things. And once you get the optimal way to do things, you just have to figure out, like, this is kind of like a bubble sort, but how do I do it in O of, or how do I make the swap in O of 1 instead of bubbling through the whole thing? Okay. So we're going to have an index, we're going to have a result, and we're going to have an index of where we are writing to. And then we're just going to go number by number and write it into the first available spot, and then figure out like how far did it need to go. So we'll start here, and we do have a 1. So we do need to move this. And so our algorithm will actually handle this. Like in this case, we don't actually need to move it, but the nice thing is we can have a general algorithm where we do move it and it'll cost us nothing. So we'll say basically, okay, whatever this index is, we need to move it to wherever we're writing to, which in our case is the last element. So this is going to cost us nothing, right? We're moving from 9 to 9. So our result will be 0. Then we go to this element, and we'll have another color. So this is going to be the color of where we're writing to, and then the green will be the color of where we're writing from. So we now need to be, this is the next available 1 slot. So here it's a 0, so we don't need to do anything. 0, don't need to do anything. 0, don't need to do anything. Okay, now we reach a 1. So essentially we need this 1 to go over here. So how many swaps is this going to take? It's going to take 1, 2, 3. So we need to add 3. And now, like I said, we're basically going to, we don't even need to even write it in. We can just record the number of operations, right? We can just say like, this is going to take 3 operations, and we can keep going. So it's going to simulate as if we wrote it in, but we don't actually need to even write it in, right? So then what's going to happen is we are going to, like, our next available slot now is over here. And now we are at this one. So it's going to be a little harder to read because I didn't actually make the swaps. Like, you don't actually have to make the swaps. You basically just have to say like what's the next available location if I was to make the swaps. So here, we need this one to go in here. Actually, I think I will represent it, even though we're not going to be doing it in the code, just because it's going to be a little bit cleaner, right? So essentially what we did here is we have something like this now, and this is a 0. So like I said, this is not necessary in the code, but I will just show it in the picture to make it easier to see. So we need this 4 to be in here, right? And once again, our idea is we're only swapping with zeros. So even though we're swapping, we're not moving any of the ones back. We're not doing any redundant work, right? You don't want to be moving any ones back. You just want to be moving zeros back and ones forward. That's the ideal operation. So this 4 needs to go over here. That's going to take 3 swaps. So we'll add another 3. So essentially swap those. Then our next available spot to write into is going to be over here. And our next number will be over here. It's a 0. We don't need to do anything. Okay, now we hit a 1. So we need to be writing over here. That's going to take 4 operations. So we add 4. And now we will replace it. So this is going to be a 1. But yeah, hopefully you see why you don't need to actually replace the numbers. You can replace them in your code. It's basically doesn't cost you anything if you want to. But it's not necessary. All you need to record is the actual index of where you're writing to. So now that this is a 1, we need to, this is the next available index. And then we go over here. It's a 0, so that's fine. Now we need this 1 to go over here. And that's going to cost us 1, 2, 3, or 5 operations. And we'll do our final swap. So we have 1 here and we have a 0 here. And we have a complete answer. And so yeah, the nice thing is if you are writing a number to the same index that you're at, like our algorithm will be able to handle that. You don't need to worry about it. It'll just cost us 0. And that's kind of basically the algorithm is you start from the right and you write your 1 into the most the rightmost available slot. And then the number of swaps is just the distance between those two. And that's basically it. So now we can code it up. So we are going to have like a write to where like our available, or we can call it like available 1 maybe, available slot. And then we'll make the first available slot equal to length of s minus 1. We'll have a result equal to 0. And so this is a string, so you have to check for actually 1 characters, not 1 numbers. So we'll say for I in range length s minus 1, start at the last character and go, so we're going to go backwards, right? And basically we're going to say if si equals 1, then we need to write it into the first available slot. Like I said, we don't actually need to write it. We just need to record how far it would need to go. So it's going to be a result plus equals, and this is going to be, so wherever we're writing into, like let's say we have an array, and this is like index 0, index 1, index 2, index 3, index 4. If we're writing from 0 to 4, we need to move it 4 slots, right? If we're writing from 1 to 4, we need to move it 3 slots and so on. So it's going to be where the index of where you're writing to, which is just available slot minus the current index where we're at. And then we need to update our available slot to be the one to the left of it, right? So whenever you write a 1, the next available slot is to the left of that. Available slot minus equals 1, and we can just return the result here. And that should be it. So let's see. Yeah, okay. Okay, and you can see it's pretty efficient. There's not too many solutions here. But yeah, the main thing about this problem is it's kind of hard to visualize the optimal movement of your numbers in your head. So just draw out a couple examples and you can figure it out from there. And then basically the idea is, you can't do like a bubble sort because bubble sort will be n squared. So how can I make it faster? And like, okay, look, if I just make it so I swap 1s with 0s, which is the optimal thing anyway, then I don't actually need to swap them 1 by 1. I can just move it to the end right away and just calculate how long it moved. So this is going to be time here is going to be O of n, and the space will be O of 1 because we're not using anything else. Oh yeah, and that's going to be all for this one. So hopefully you liked it. If you did, please like the video and subscribe to the channel. And then I'll have videos for the last 2 problems in the contest pretty soon. So stay tuned for those. And thanks for watching.